Hello and welcome to this lesson for A-Level Physics on the OCR specification looking at Module 3, Forces and Motion. We're looking at the subchapter of Forces in Action and the topic of density. So in today's lesson we're going to be looking at how to calculate the value of density. So if we've been successful and we've learned in today's lesson, we should be able to know the definition of density, calculate the value of densities, and know the value of density can be estimated from the volume of a material. So we're going to be looking at the following part of the OCR A-Level Physics specification. 3.2.4 Density and Pressure, looking at this subtopic of A, density. So the density is the amount of matter in the substance in a certain volume. So density is how much mass of a material there is in a certain volume. So you could think of this as a measure of the number of particles in a certain volume, or it's a measure of the space between the particles in a certain volume. Now this tells us that density could be thought of as a measure of how spread out the particles are in a certain volume for a substance. So if an object is very dense, it means that it has lots of particles per unit volume. So if the object is very dense, there are small gaps on average between the particles in the substance. Now if an object is not very dense, then it has very few particles per unit volume. So what that means is if an object is not dense, there are large gaps on average between the particles in the substance. So we can think of density as the mass of a substance in a unit volume. So therefore, we can calculate density with the following equation. Density is equal to mass divided by volume. Now, if we wanted to use our standard units, we would say that density is measured in kilograms per meter cubed, with the mass in kilograms and the volume in meters cubed. So therefore, you could also think of density as the mass of 1 cubic meter of a substance. So for example, gold has a density of 19,300 kilograms per meter cubed. So it means that 1 meter cubed of gold has a mass of 19,300 kilograms. Now, the units of density tend to be kilograms per meter cubed, but it doesn't always have to be that. The unit of density can always be written as the unit of the mass divided by the unit of the volume. So if the mass was in grams and the volume is in centimeters cubed, the unit of density will be grams per centimeter cubed. Now the density of an object is only dependent on what it is made from. So the density of a material does not vary with either size or shape. So as we mentioned before, an object is very dense if it has lots of particles per unit volume, and an object is not very dense is if it has few particles per unit volume. So we can now relate this to the particle model of matter. So this shows us the idea that solids have a higher density than liquids, and liquids have a higher density than gases since they have more particles per unit volume. Or you could think of it as that solids have a higher density than liquids, and liquids have a higher density than gas since there's greater space between the particles per unit volume. But fundamentally, the solids are high density, the gases are low density, and they're an increase in density from gases to solids. Now technically, a vacuum has a density of 0 kilograms per meter cubed, as there are no particles in the volume at all on average. Now, density is a very important property in the real world because density can determine if an object floats or sinks. So if an object has a higher density than the fluid it is in, it will sink. If an object has a lower density than the fluid it is in, it will float. Now, water has a density of 1 gram per centimeter cubed. This means that can be used to determine if a material will sink or float in water. So you could think of 1 gram per centimeter cubed as that 1 centimeter cubed of water has a mass of 1 gram. So let's have a look at how to calculate density. So if we've got a mass of 6 grams in a volume of 2 centimeter cubed, what is the density of the substance? So the density is the mass divided by the volume. So it's 6 grams over 2 centimeter cubed. So therefore the density is 3 grams per centimeter cubed. But what if you're not given the volume of the object? Now, if the shape is regular or symmetrical, we can find its volume by using one of the equations you use in mathematics. So for example, the volume of a sphere is 4 pi r cubed, where r is the radius of the object. The volume of a cube is L cubed, where L is the length of the object, and the volume of a cylinder is pi r squared times by h, because h is the height of the object. So let's have a look at a different question now. If we have a mass of 20 grams in a sphere with a radius of 4 centimeter cubed, what is the density of the substance? So you can say density is mass over volume. Then you can work out the volume of the object with the mathematical equation, 4 over 3 pi r cubed. Pop in the values. You can then say density is the mass, 20 grams, over the volume, 268 centimeters cubed. So the density is 0.075 grams per centimeters cubed. Now, densities can be very useful to identify materials in the real world. If you have an unknown solid substance in a material or an object, you can use the value of density to identify the material. So every solid material has the same density regardless of object dimensions. So if you can calculate the density of a solid material, you can work out what the material is. So here, for example, you can see some different examples of densities of different solid materials. So for example, aluminium always has a density of 2.64 grams per centimeter cubed regardless of the object shape that it has. So if you can work out the density of a material, you can identify what the material is. Now you must be able to work out the density for objects which are either regular or symmetrical, or irregular or non-symmetrical. Now for both types of objects, the mass is measured with a balance. The mass of any object is always measured with a balance. Then you can work out the volume, but for a symmetrical or regular object with a mathematical equation. So with the regular shape, consider something like a 3D symmetrical shape like a cube, but it can be carried out for any regular 3D shape. You can calculate the volume by measuring the different dimensions, so in this case the lengths of the cube. So you can measure length 1 here, then length 2, then length 3. We know that because it's a cube, the volume is the length 1 times by length 2 times by length 3. Then we have our mass, we've worked out our volume, so density is mass over volume. We can work out the density of this regular shaped material. But what about an irregular shaped object? Once again, we measure the mass with a balance. But to find the volume of an irregular shaped object, we must use a method called water displacement. So we put the object in a measured amount of water and measure how much the water rises. The difference is the volume of the object. We can then measure the mass using the balance. And then from this, we can calculate the density of the object. So consider a beaker of water. You can place the measured object in this beaker of water. The object will displace its own volume of water in the beaker. So therefore it will cause the water level of the beaker to rise, and the difference it rises is the volume of the object. So how much this water level rises can be considered to be the volume of the fully submerged object. So the change in the water level gives you the volume of the object. You observe this effect when you get into a bath or you put dishes into a sink full of water. So for example, if we start off with a beaker of 300 mils of water, we fully submerge an object into the beaker and it rises to 500 mils. Well, therefore the volume of the object is 200 mils, because 500 minus 300 equals 200 mils. If we then know the mass of the object, so for example we could say the mass of this object measured with the balance was 200 grams. We would say density is mass over volume. 200 grams over 200 centimeter cubed is 1 gram per centimeter cubed. Now, alloys must have their densities calculated slightly differently. That's because alloys are a mixture of two or more metals. Now, whilst the volume of a substance is not affected by the mixture of the different particle types, the mass of the object is affected. So it's a very important idea. So we must consider the density of different types of metals. So for example, for an alloy of volume V with two metals made up in the alloy, A and B, we can consider the volume of metal A to be volume A, and the mass of A to be the density of A times by the volume of A. And we consider the volume of metal B to be VB, and the mass of B to be the density of B times by the volume of B. This is coming from the equation that mass equals density times by volume. We can then use this to work out the density of the alloy, because density is mass over volume. So we can say V is going to be the total volume of the alloy. Now we can say that the total mass over the total volume equals the total density of the alloy, which you can calculate the total mass by doing the density of one of the metals times by the volume of one of the metals, plus the density of one of the metals times by the volume of the other metal. So if you look at this particular equation, the term rho AVA plus rho BVB is the total mass of the two metals in the alloy. So let's have a look at an example of how this works. Brass is an alloy which consists of 3.3 times 10 to the minus 5 meters cubed of copper and 1.7 times 10 to the minus 5 meters cubed of zinc. What is the density of brass when the density of copper is 8,900 kilograms per meter cubed and the density of zinc is 7,100 kilograms per meter cubed? So you work out the mass of the copper by doing the density of the copper times by the volume of the copper. So you work it out to be 0.294 kilograms. You work out the mass of the zinc by doing the density of the zinc times by the volume of the zinc, so it's 0.121 kilograms. The total mass is the mass of the copper plus the mass of the zinc, so it's 0.415 kilograms. The total volume is the total volume of the copper and the zinc, so it's 5 times 10 to the minus 5 meters cubed. So therefore the density is the total mass over the total volume, so it's 8,300 kilograms per meter cubed. And that's how you work out the density of an alloy. So that brings us to the end of this particular lesson. So in this lesson, we've looked at the concept of density and how to work it out with the equation rho equals m over v. So if we've been successful and we've learnt in today's lesson, we should be able to know the definition of the term density, calculate values of density, and know the value of density can be estimated from the volume of a material. So thank you for watching this particular lesson for A-Level Physics on the OCR specification. We was Module 3, Forces in Motion, in the subchapter Forces in Action on the topic of density. Thank you very much and have a lovely day. Hello and welcome to this video for A-Level Physics in the OCR specification on Module 3 Forces in Motion in the subchapter Forces in Action on the topic of pressure. So in today's lesson we're going to look at what pressure is and how to calculate different pressures. So if we've been successful and we've learned in today's lesson, we should be able to know the definition of pressure, calculate values of pressure, and then calculate values of forces in area based on the pressure exerted. So we're going to look at the following part of the OCR A-Level Physics specification, 3.2.4, density and pressure, and looking at the idea that learners should be able to demonstrate and apply their knowledge and understanding of pressure with pressure equals force over area for solids, liquids and gases. So, pressure is produced when a substance exerts a force over a particular area. So this could be when a solid material is in contact with another solid material. Or it could be when a fluid's particle, so a liquid or a gas, collides with the surface or containers they are in. So there are two main types of pressure. We've got surface or solid pressure, which is the pressure exerted when a solid object places a force on a surface. But you've also got fluid pressure as well. So that's the pressure exerted when the particles of a fluid collide with the surface or a container. So just to clarify, we'll look at the concept of fluid pressure in more detail. So fluid pressure, as we said, is the pressure exerted when the particles of a fluid collide with a surface or container. Now the fluid can either be a liquid or a gas. Now it's important to note that the definition of a fluid is it's a substance that flows. Now in a fluid, the particles will have a random motion with a range of speeds. This means that in a fluid, all the particles are moving around in random directions. So the particles in the fluid will collide with the sides of the container or the surface as they move around. Now because it is random, this means that all sides will roughly have the same number of collisions as the particles are moving freely. Now it can be considered that these collisions cause a pressure in the fluid. Now we know that because of the direction of the collision, the pressure will always act outwards on a fluid. So we can say that the fluid produces a pressure which produces a force normal to the surface or the containers. So the force is at a right angle to the surface that the pressure is exerted on. So just to clarify, fluid pressure, which is pressure in a liquid or a gas, is the pressure exerted when the particles of a fluid collide with a surface or a container. And the pressure in the fluids causes a force normal to any surface. Now, we can work out the pressure with the following equation. Pressure in pascals is equal to the force normal to a surface in newtons divided by the area of that surface in meters squared. Now, the units of pressure can also be expressed in terms of force and area. So, for example, when the force is in newtons and the area is in meters squared, we call the unit of pressure the newtons per meter squared, or in this case, the pascal. But when the force is in newtons and the area is in centimeters squared, the unit of pressure is newtons per centimeter squared. And when the force is in newtons and the area is in millimeters squared, the unit of pressure is newtons per millimeter squared. Now, this is an equation which you've got to be able to use and memorize for your examination. Now, you must have to convert the area into meters squared to find the pressure in pascals, but do be aware that some questions can ask for the pressure in different units. And you'll also be expected to rearrange this equation to make the area or the force the subject of the equation. So, for example, it's a common rearrangement to see the equation in the form of the force normal to a surface in newtons is equal to the pressure in pascals times by the area of that surface in meters squared. So what this tells us is that a resultant force can actually cause a change in pressure. So we can write it out as well as the resultant force in newtons is equal to the change in pressure in pascals times by the area of the surface the force acts upon in meters squared. So here's an example calculation. A gas inside a container applies a force of 400,000 newtons. Now, the walls of the container have an area of 8 meters squared. Calculate the pressure of the gas. So we can calculate the pressure with the following equation. Pressure is the resultant force over the area of the surface. So it's 400,000 divided by 8. So the pressure is 5 times 10 to the 4. It can be written in pascals because the force is in newtons and the area is in meters squared. So, to summarize what we've learned in today's lesson, we should be aware of the definition of the term pressure. We should know to calculate pressure, it is force over area for solids, liquids and gases. So, if we've been successful and we've learned in today's lesson, we should be able to state the definition of pressure, calculate values of pressure, and then finally calculate the values of force and area based on the pressure exerted. So, thank you for watching this lesson on Module 3 of OCR A-Level Physics on Forces and Motion in the subchapter 3.2 Forces in Action and on the topic of pressure. Thank you very much and have a lovely day. Hello and welcome to this video for A-Level Physics in the OCR specification in the module of Forces and Motion and in the subchapter of Forces in Action, looking at the topic of Archimedes' Principle. So in this lesson we're going to look at Archimedes' Principle and how to apply Archimedes' Principle to different situations. So if we've been successful and learned in today's lesson, we should be able to state what Archimedes' Principle is, detail how upthrust is produced, and know how to calculate upthrust and pressure in fluids. So we're going to look at the following part of the OCR A-Level Physics specification, 3.2.4 density and pressure, and we're going to be looking at particularly at C, which is pressure is equal to H rho G, the upthrust on an object in the fluid, and Archimedes' Principle. Now, look at the following schematic diagram of a dam. This is an example of an open system of a fluid. So think about the following. How are dams constructed and why is this? Now if you look at the picture, you'll notice that dams are constructed with a thicker wall at the bottom and a thin wall at the top of the dam. That's because fluid pressure changes in an open system. So it's a fundamental concept of pressure. Fluid pressure changes in an open system, but it stays the same in a closed system. So you can see here that there is a low pressure at the top of this liquid, which requires a thin wall, whilst there's a high pressure at the bottom of the liquid, so requires a thicker wall. So we can see very quickly that fluid pressure increases with depth in an open system. So as we move down the wall, there's an increasing pressure as we go to a greater depth of fluid. So this shows us that in open systems, the pressure of a fluid increases with depth. And this can be shown in larger areas of water, like an ocean. So you can see here that there is a liquid, and the force being placed downwards increases the lower you go, as there's an accumulative effect from the particles above it. So this downward force that's being produced is weight, and the further down you go, the more particles there are above you in the fluid, so the greater the weight above you. So you'll see at the top of the fluid it's got a lower pressure, because there are only a few particles above that particular point pushing down, so the weight pushing down at that part is low. But at the bottom we have a higher pressure because there are more particles above that point pushing downwards, so the weight pushing down is high. So we can see that as we move down our fluid, that the weight of the fluid acts downwards on an object increasing with depth, and the pressure acting downwards on the object increases with depth, because the lower you go in any fluid, there are more particles above you pushing downwards from the collisions that they make. So what this actually means is that at any horizontal line in a diagram of a fluid, the number of particles above that point is roughly the same. So it tells us that along that particular line, the pressure along it is constant. Now, when this is considered in air as a fluid, the horizontal line of constant pressure is called an isobar. Now, it's important to note that areas of different pressure can exert a force on objects in the fluid. So if you're at the bottom of the ocean, a force is exerted downwards, pushing you down. So to clarify, in an open system, the fluid pressure increases with depth. That's because the further down in a fluid you go, the greater the number of particles above that point producing a force downwards. Now, in an open system, the fluid pressure is constant in a horizontal line of the same depth, because along this line there's the same number of particles producing the same force pushing down. Now, a difference in pressure can cause a resultant force on an object, which can be calculated with our equation of a resultant force is equal to a change in pressure times by the area. Now, this concept is shown in the following diagram. Now, you can see in this particular image that because pressure increases with depth, at the top of the column there is a lower pressure, so you get a little spurt of water, but at the bottom there's a large spurt, so there's a higher pressure. Why is that? At the top there is less weight above it pushing down, and at the bottom there's a higher pressure because there's more weight above that point pushing downwards. Now, we can calculate the pressure in an open system with the following equation, that the pressure change in pascals is equal to the change in depth in meters times by the density of that fluid in kilograms per meter cubed times by the strength of gravity in meters per second squared. Now, this equation calculates how the pressure changes when an object moves from one position to another in the fluid. Now, the equation of pressure in pascals equals the depth in meters times by the density of the liquid in kilograms per meter cubed times by the strength of gravity calculates the pressure at one point in the fluid. Now, we can derive this as consider the following column in the fluid. The pressure at the base of this particular column is going to be force over area, so therefore the force in this instance is weight, so the pressure is weight over area. Now, we know weight is equal to the mass that's in the column times by g, the strength of gravity. Now, we also know that mass is also equal to density times by volume. So weight is density times by volume times by g. Volume is the area times by the height, so it is it's going to be rho times by a times by h times by g. So therefore pressure is going to be this value for weight over area, and you'll notice straight away that the a's cancel through, so therefore pressure is equal to rho gh, or density of fluid times by the strength of gravity times by the depth. Now, this equation tells us a few things. Pressure does not depend on the cross-sectional area of the object. pressure does increase with depth. Denser fluids exert greater pressures, and that the pressure for a fluid at a depth is the same in all directions. So let's have a look at an example question. Calculate the pressure due to seawater of density 1050 kilograms per meter cubed at a depth in the sea of 200 meters. So we can calculate the equation. Pressure with the equation pressure equals depth times by density times by strength of gravity. So 200 times by 1050 times by 9.81. So pressure is equal to 2.1 times 10 to the 6 pascals. Now, if an object is less dense than the liquid it is submerged in, it will float. So the density of an object determines if it will float or sink. So if an object is denser than the liquid it is submerged in, it will sink. Now, why does density determine if an object floats or sinks? How does this link into forces on an object? So the buoyancy of an object depends on the forces that act upon it. An object will float if the upthrust being produced is equal to the weight. That's because the forces on the object in the vertical plane are balanced. There's no resultant force. However, an object sinks if the weight is greater than the upthrust. That's because the force on the object in the vertical plane are unbalanced. There's a resultant force downwards. Now, if the upthrust were greater than the weight, then the object would accelerate out of the liquid, as there'd be a resultant force upwards, but this can't happen due to how the forces are produced on the object. An upthrust would only be produced when submerged in the fluid. So, what actually causes upthrust to be produced on an object immersed in water or a fluid? Well, it's linked into what we've just looked at. When an object is in water, there's a greater pressure on the object at its bottom than at its top. This difference in pressure makes the object push up. It creates a resultant force called upthrust. So because there's an increase in pressure the further you go down, there's a higher pressure at the bottom of the material compared to the top of the material. Now this produces the upthrust, and there's always a force exerted going from the higher pressure to the lower pressure. Now, like we said, for all liquids, pressure increases with depth, because the further down you go, the more particles above you pushing down. Now we can calculate upthrust as the force on the top surface is pressure times by area, so it's rho GH times by A. Whilst the force at the bottom surface again is pressure times by area, so it's rho g times by h plus x, the increased distance, times by a. So the resultant force is the two forces subtracted from each other, so is equal to a rho g x. So that is what our upthrust is equal to, a rho g x. So the volume of a block of fluid displaced is AX, and it has a mass of AX rho g. Now, an object that is less dense than the fluid it is placed in weighs less than the equivalent volume of the liquid. Now that's very, very important, because it means that it displaces a volume of fluid that is equal to its weight. So therefore upthrust equals weight, and it does that before it is completely submerged in the fluid. So an object that's denser than the fluid is placed in will weigh more than its equivalent volume of fluid that it would in theoretically displace. This means that the object is unable to displace enough fluid to equal its weight when it's in the actual fluid. So this means that the weight is always larger than the upthrust, so will always sink. So this leads to the concept of Archimedes' principle. This is that the upthrust exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. So for an object to float, the weight of the object must be equal to the weight of the fluid it displaces. Now, an object will float on a fluid if it has a lower average density than the fluid, because the object will only displace a volume of fluid that weighs as much as the object does. The volume of fluid is lower than the volume of the object due to the different densities, so it will be partially immersed when this occurs. But if the object is denser than the fluid, the water it displaces will always weigh less than the object itself, causing it to sink. So for a floating object, we can write this mathematically, as we would say h2 minus h1 rho ga equals rho vg, because you can see that the change in height times by the area is the volume. That will equal the weight of the object, which is mg. Now let's just quickly look at the idea of air pressure. Now if you live in the atmosphere of the Earth, you're constantly surrounded by the particles of the air. Now these gas particles constantly move about at random. The air is a fluid as it can flow since the particles are able to move around. Now in this motion, some of the particles will collide with the objects present. And when it does this, these collisions will cause a force to be exerted on those objects. This produces a pressure which we call the atmospheric pressure. Now the pressure means that the force is exerted at right angles to any surface which the particles will hit. Now atmospheric pressure works in the same way as the fluid pressure in a liquid discussed previously. At the top of the air gas, there are few particles above pushing downwards exerting a force, while there are many particles above pushing downwards exerting a force when you are at the bottom of that gas at the surface. So at the top of the atmosphere we have a low pressure, and at the bottom of the atmosphere near the surface we have a high pressure, which you can see in this diagram. So the higher up you go in the atmosphere, there is less weight pushing downwards exerting a pressure. But there's also a second reason why this takes place. There are fewer particles pushing down as you are higher up in the atmosphere, and at this point there are fewer particles in the atmosphere in general. So there are fewer air particles in total above the point you are measuring. That's because the atmosphere has become thinner the further up you go, because the particles are further apart. So we can also say that the density of the atmosphere has decreased with altitude. There are fewer air particles per cubic meter. So remember, there are two reasons why the pressure will change in the atmosphere: the number of particles present and the amount of force acting downwards. Also note, although we measure the height from a surface when we calculate atmospheric pressure, we do not look at depth. So this means the atmospheric pressure decreases with height. So when you go to high distance from the surface, the pressure is low. And when the distance from the surface is low, the pressure is high. Once again, why is that? Because there are fewer particles above producing a weight downwards, and the particles are further apart. Now pilots know this. The higher you fly, the lower the pressure of the atmosphere is. At the top of Ben Nevis, the highest mountain in the UK, the air pressure is 87 kilopascals as opposed to 101 kilopascals at the surface of the Earth. So, atmospheric pressure is created on a surface by air molecules colliding with the surface. The greater the number of particles above a point in the atmosphere, the greater the weight acting down from the particles, the greater the pressure. And there are fewer particles higher up in the atmosphere producing pressure as they're further apart from each other. So as height increases or depth decreases, the atmospheric pressure decreases. So that brings an end to our lesson today, where we looked at pressure is equal to density times by the strength of gravity times by the height. We've looked at upthrust on an object, and we've looked at Archimedes' principle. So if we've been successful and we've learnt in today's lesson, we should be able to state what Archimedes' principle is, detail how upthrust is produced, and know how to calculate upthrust and pressure in fluids. So thank you very much for watching this lesson for the A-Level Physics OCR specification in the Module 3 chapter of Forces of Motion, the subchapter of 3.2 Forces in Action, and finally the topic Archimedes' Principle. Thank you very much and have a lovely day. Hello and welcome to this lesson on dynamics, which is part of the Forces in Motion module for OCR A-Level Physics. So in today's lesson on dynamics, we're going to understand the different types of forces and calculate the different forces. So if we've been successful and we've learnt in today's lesson, we should be able to state the different types of forces such as tension, the normal contact force, and upthrust. Draw free body diagrams for situations and calculate the resultant force in different situations. So in today's lesson, we're going to look at 3.2.1 dynamics of OCR A-Level Physics. Now, in many situations, you need to be aware of the different forces acting on a body. Now, some of these forces you need to be aware of include weight, which is the gravitational force acting on an object through its centre of mass, which we can calculate with the equation weight equals mass times by gravity, where on Earth the gravitational field strength at the surface is 9.81 meters per second squared. We have friction, which is the force that arises when two surfaces rub against each other. We have drag or air resistance, which is the resistive force on an object travelling through a fluid. We have tension, the force within a stretched cable or rope. We have upthrust, an upwards buoyancy force acting on an object when it's immersed in a fluid. And we have the normal contact or the reaction force, which is a force arising when one object rests against another object. Now, this force comes from Newton's third law of motion, and this force always acts perpendicular to the surface. Now, all forces are measured in newtons. Now, 1 newton is defined as the force that will give a mass of 1 kilogram and acceleration of 1 meter per second squared. So 1 newton equals 1 kilogram meter per second squared. Now, to fully understand the forces acting on an object, we must draw a free body diagram of that object. Now, a free body diagram should be drawn like a scale diagram. The length of the arrow should represent the magnitude of the force, and the angle of the arrow should represent the direction the force acts. Now, the arrow should always start at the centre of mass of an object, as shown on the diagram on the screen. Now, to understand this, a free body diagram shows a single body on its own. This diagram should include all forces that act on the body, but not the forces it exerts on the rest of the world. And the free body diagram shows the resultant force acting on the body as a result of the different forces, but the free body diagram does not explicitly show the resultant force itself. Now, as forces are vector quantities, the arrow labels of the forces should show the size and the direction of the forces, as shown in the following situation of a satellite, and the next situation of a parachutist, or the next situation of a car. Now, if we consider the example of a human standing up, we can see our free body diagram. Now, as we know the human is in equilibrium, the forces must be equal to each other. So the upward forces equal the downward forces, or in this case, R will equal W. Now, when an object is in equilibrium, there is no resultant vector or force on the object. This means, if drawn correctly, the free body diagram for a body in equilibrium should form an enclosed shape when arranged into a scale diagram. Now, a scale diagram is when the vectors are placed head to tail in a scaled size to each other. So in this example, if the spider is hanging in equilibrium, then when the forces are arranged as a scale diagram head to tail, they should form an enclosed shape, as shown here. Now, an object in equilibrium can either be at rest or moving with constant velocity. Now, when objects are not in equilibrium, there is a resultant force on the object. The resultant force acting on the object will cause the object to accelerate. And we can work out the size of the resultant force, as resultant force is the inertial mass times by the acceleration, or F will equal ma. Now, if the resultant force is in the same direction as the motion of an object, the acceleration is positive. If the resultant force is in the opposite direction to the motion of the object, the acceleration is negative. Now, when objects are in equilibrium, we have said before there are no resultant forces on the object. So we can say that the overall horizontal forces equal 0, and the overall vertical forces equal 0. So if an object is in equilibrium, the sum of the components in each direction, horizontal or vertical, must equal to 0. So if it's in equilibrium, we can say that R minus W equals 0, which allows us to rewrite it as R is equal to W. In this example here, if our object's in equilibrium, we can say that T minus D equals 0, which we can rearrange to say T equals D. Now, when asking to calculate a force on an object in equilibrium, you must carry out the following procedure. The first step is to draw the free body diagram of the object. The second step is to identify the forces acting in just the horizontal or the vertical. The third step is to identify the forces acting at an angle, and resolve these forces into horizontal and vertical components. You would then balance the horizontal and vertical forces on the object to find the desired force you require. Now an example of this is as follows. A child of weight W on a swing set is at rest due to the swing set being pulled to the side by a horizontal force F1. The rope supporting the seat is at an angle theta, and assume the child is at equilibrium and the seat has no weight. Write an equation for theta. So the first step is to identify the forces in either the horizontal or the vertical. So F1 is in the horizontal and W is in the vertical. The next step is to identify the forces at an angle and then resolve them into horizontal and vertical components. So T is at an angle, so it must be at the vertical and it must be in the horizontal. Now the sine and cosine values for the horizontal and vertical components of T have been reversed, as the angle measured has also been reversed from the horizontal because it's coming from the vertical. So therefore we can say the vertical component is T cos theta, and then the horizontal component is T sine theta. You can do that by drawing out your triangle and using your trigonometric identities for sine and cosine. The third step is to equate the horizontal and vertical components. So we can say horizontally that F1 minus T sine theta, because they're in opposite directions, is equal to 0. And then vertically, W minus T cos theta is equal to 0. We can then rearrange them to say horizontally F1 is equal to T sine theta, and vertically W is equal to T cos theta. So if we then use that to work out our value of theta, we know that sine divided by cosine is equal to tan. So tan theta equals sine theta over cos theta. So F1 over W is equal to T sine theta over T cos theta. The T's will cancel through and sine over cos becomes tan. So F1 over W equals tan theta. So arctan of F1 over W is equal to theta. And there we've answered our question. So to summarise what we've looked at in today's lesson, the net force or resultant force is equal to mass times acceleration, F equals ma. The Newton as a unit of force, then the weight of the object is equal to W equals mg. The terms tension, normal contact force, upthrust and friction, free body diagrams, and one-dimensional and two-dimensional motion under a constant force. So if we've been successful and we've learnt in today's lesson, we should be able to state the different types of force such as tension, normal contact force and upthrust, draw free body diagrams of different situations, and calculate the resultant force in different situations. So thank you so much for watching this lesson on dynamics, which is part of the Forces and Motion module in OCR A-Level Physics. Thank you so much and have a lovely day. Hello and welcome to this video on nonlinear motion, which is part of the Forces and Motion module in OCR A-Level Physics. So in today's lesson, if we are being successful and we've learnt in today's lesson, we should be able to understand the concept of drag for a body undergoing motion, be able to detail the motion of objects in the presence of drag, and finally we should be able to describe the concept of terminal velocity. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification: motion with non-uniform acceleration. So when an object moves through a fluid, it will experience a drag force from the fluid. Now drag is a frictional force that opposes the motion of the object. Now the drag force experienced by an object moving in the air is called air resistance. Now the drag force is linked to the force required to move the particles of the fluid, such as air, out of the path of the object every second. Now the lower the drag force, the higher the top speed of our object. The lower the drag force, the lower the amount of fuel used on a journey if that object is powered by an engine. Now it's important to note that drag forces can never speed things up or start something moving, but drag forces do convert kinetic energy stores into thermal energy. Now the size of the drag force depends on different factors, such as the speed of the object, the shape of the object, the density of the fluid, and the texture of the object. Now the most important factors are the cross-sectional area of the object and the speed of the object, where the larger the surface area of the object, the larger the drag force it experiences. And the faster an object moves, the greater the drag force the object experiences. Now our drag force is directly proportional to the speed of the object squared. So when the speed of an object is doubled, for example, the drag force increases by a factor of 4. Now the size of the drag force experienced by an object determines whether an object is accelerating or not. Now a velocity time graph can be used to work out if an object is accelerating by looking at the gradient of the graph. So here we have an example of a velocity time graph, with one area showing a straight line and the other area showing a flat line. Now this allows you to determine if an object has a resultant force acting on it. So you'll see with our straight line we have a constant gradient, and with a flat line we have no gradient. Now we remember that the gradient of a velocity time graph is the acceleration of the object. So our first section shows constant acceleration, and our second section shows no acceleration. Now only a resultant force acting on an object can cause an object to accelerate. So we know in our first section of our graph we have a resultant force. In our second section of the graph there is no resultant force. So let's now consider the velocity time graph of an object that is falling in a fluid. Now an object falling through a fluid, a liquid or a gas, initially accelerates due to the force of gravity. Eventually the resultant force will be zero and the object will move at a constant velocity. So if a falling object has no acceleration, it has reached its maximum velocity and we call this terminal velocity. So let's look at this in a bit more detail. There are three stages to any falling object's journey. The first stage is when an object first falls. Weight is larger than air resistance, there's a resultant force downwards, so it accelerates downwards. So at the instant an object starts to fall, there is no drag force on the object, so therefore the total force of the object is equal to the weight. So the acceleration of our object is g, the acceleration of free fall. Now when the object then moves through the fluid, a frictional force drags on it. These drag forces always act in the opposite direction to an object's movement. These drag forces increase with the object's speed. Remember, the greater the speed, the greater the frictional force. And these drag forces depend on the shape and size of the object. It's important to note that streamlining an object reduces the drag force it experiences. So you can see here that our resultant force is linked to both the weight acting downwards and the air resistance against the motion. Now a resultant force causes an acceleration in the direction of the resultant force, which is Newton's first law of motion. So here in this example, the object accelerates downwards as there's a resultant force acting downwards, which we can see here that the air resistance or the drag is a lot less than weight, so therefore we will have our resultant force. Now the effect of gravity, which produces this weight, produces an acceleration, like we said, of 9.81 meters per second squared. And the effect of gravity, which produces the weight, stays constant throughout the process. So if an object accelerates only due to the force of weight, we do say it is falling freely. However, the object will always accelerate at a slower rate than this, since the acceleration is directly proportional to the resultant force. The resultant force is smaller than the weight due to the effect of air resistance acting against this motive force. So we can see with our velocity time graph we have our straight line in our first section. So here we've got a constant positive gradient and we've got a constant acceleration. This leads on to stage 2, because as the object increases in velocity, the air resistance increases as more air particles are pushed out of the way per second. This decreases the resultant force and the acceleration, as shown in this particular diagram. So as we can see here, our air resistance is now a lot larger, so our resultant force is going to be a lot smaller. So the object is still accelerating, but at a slower rate. The resultant force and the acceleration it causes for the object are directly proportional for an object with constant mass, which is Newton's second law of motion. So as the resultant force decreases, the acceleration it produces decreases. So the object is still accelerating, is still getting faster, but at a slower rate. So you observe this in our velocity time graph, with a curving line downwards, because the gradient of the line is decreasing, the acceleration is decreasing, but the velocity is still increasing, but at a slower rate. This leads on to stage 3. Eventually the air resistance is the same size as the weight, so the velocity of the object stays the same, and this is our terminal velocity. So as you can see in this diagram, so now air resistance and weight are the same size, there is no resultant force, our object is not accelerating. When there is no resultant force on an object, the object has no acceleration. The object maintains the same speed with the same direction. So if the object is already moving, it will keep moving. The object maintains a constant velocity. The object has inertia. At terminal velocity, the potential energy of an object is transferred as it falls to the internal energy of the fluid via the drag force. The terminal velocity of a falling object, as we said, depends on its shape and area. So the accelerating force acting on all falling objects is weight, and would make them fall all at the same rate if it was not for this air resistance. So we can see this on the following section of our velocity time graph. The flat line has a line of gradient 0, so it has no acceleration. It has a constant velocity, which is not 0, so we say it has a terminal velocity. So when an object falls, our weight stays constant, but the resistive force of air resistance changes in size at different parts of the journey. So remember, we have our 3 stages of when an object first falls, weight is larger than air resistance. So there's a resultant force downwards, so it accelerates downwards. But as the object increases in velocity, the air resistance increases as more air particles are pushed out the way per second. This decreases the resultant force and acceleration. Eventually, the air resistance is the same size as the weight, so the velocity of the object stays the same. This is terminal velocity. So we can see this in our 3 stages of our velocity time graph. So in our first stage, we know that force is equal to mg, so acceleration is going to be equal to g. In our second stage, F is equal to mg minus d. So A is equal to mg minus d over m. And in our third stage, the force is equal to 0 and our acceleration is equal to 0. Now, if the object was falling through a liquid instead of air, the resistive force generated by a liquid is larger, as the particles are more densely packed compared to air. So this means a falling object reaches stage 3 faster. Now, if the object was falling through a liquid instead of air, the resistive force generated would be larger, so this means that the falling object would need to fall much further through the air compared to water to reach terminal velocity. So on the moon, where there's little atmosphere, all objects will hit the ground together. But on the Earth, air resistance causes things to fall at different speeds, and the terminal velocity of any object is determined by its drag in comparison to its weight. So the frictional force depends on the object's shape and the object's area. Now we can determine the terminal velocity of an object falling in a fluid. A ball can be dropped in a tube of cooking oil, and the ball will fall through the oil down to the bottom of the tube. So you'll see we have our fluid resistance acting against motion and our weight acting downwards. So the object is dropped through a fluid, and the object is timed as it falls through the fluid with a stopwatch. The time is recorded at marked distance intervals in the fluid, and then the distance travelled and the time taken measured are used to determine the velocity of the object at different parts of the fluid. The velocity of the object, including the terminal velocity, is then determined for the journey. Now the object will maintain this terminal velocity until it hits the bottom of the cylinder. Now throughout the journey, the weight acting on the object stays constant, but the resistance it experiences changes. Now if there was no fluid, the object fell in a vacuum, there will be no resistance, so the object will constantly accelerate down due to weight. Now it is very difficult to measure the terminal velocity of an object, so this experiment would get inaccurate results. So it's very difficult to measure when the object would have actually obtained terminal velocity, as it's difficult to measure the timings of an object falling as it occurs very quickly. To solve this, you can use computer sensors and light gates, as this would reduce your uncertainty in your time and measurements, as it would mean that the random error produced would be smaller. Now it is also unlikely in any class experiment that the object would have achieved terminal velocity, as it takes a relatively long time of falling to achieve terminal velocity. So to solve this, you would have to increase the height at which the object falls in a fluid. Now all objects when falling in a fluid for long enough time will achieve terminal velocity. The fluid could be oil, could be water, could be air, but it's important to note that the denser the fluid, the greater the drag force generated, the faster the object will reach terminal velocity. So to summarise what we've looked at in today's lesson, we've looked at the drag as the frictional force experienced by an object travelling through a fluid, the factors affecting drag for an object travelling through the air, and the motion of objects falling in a uniform gravitational field in the presence of drag. We've looked at terminal velocity and the techniques and procedures used to determine terminal velocity in fluids. So if we've been successful and we've learnt in today's lesson, we should be able to understand the concept of drag for a body undergoing motion, detail the motion of objects in the presence of drag, and describe the concept of terminal velocity. So thank you for watching this lesson on nonlinear motion, which is part of the Forces and Motion module in OCR A-Level Physics. Thank you so much and have a lovely day. Hello and welcome to this video on the topic of moments, which is part of the Forces and Motion module for OCR A-Level Physics. So in today's lesson, what we're going to be doing is we're going to be looking at moments and how to calculate moments on different objects. So if we've been successful and we've learned in today's lesson, we should be able to describe the conditions under which a force produces a turning effect, describe the support force on a pivoted body, and understand that the forces and moments on a body can be in equilibrium. So we're going to be looking at the following part of the OCR A-Level Physics specification: 3.2.3 Equilibrium, in particular, moment of force and the principle of moments. Now, linear forces are forces which make objects accelerate in straight lines. So this is acceleration by changing speeds. Now, rotational forces are forces which make objects accelerate in a circular path. So a rotational force or a system of rotational forces may cause an object to rotate. So this is acceleration by changing direction. Now, if we consider the following object, the object is fixed at point X. We can place a force downwards on the object. Now remember to always draw the force of the weight from the centre of mass of the object in free body diagrams. Now we call the fixed point on an object the pivot or the fulcrum. Now an example of this is the point where an object is screwed into a wall. So in this example, point X is the fulcrum of the pivot. Now, whilst the force is acting vertically downwards on the object will actually rotate due to this force. Now, this is due to the object being fixed in position at a point. So this causes the force to have a rotational effect on the object. So the resultant force is causing the object to accelerate by changing direction. So whilst the force is acting vertically downwards on the object will actually rotate due to this force. Now, the effect of a force causing rotation, or the turning effect, is known as the moment of the force. Now, the moment of a force depends on two quantities: the magnitude of the force, now the bigger the force, the greater its moment, and the perpendicular distance of the force from the pivot. The further the force acts at the pivot, the greater its moment. Now, we can calculate the moment of a force with the following equation. Moment is equal to force times by perpendicular distance from the pivot. Now, the perpendicular distance is the distance of a parallel line between the force and the pivot. Or a better way to say it would be the distance of a parallel line between the line of action of a force and the pivot. Now, it's always important that when you're calculating the moment of acting on an object to always use the perpendicular distance. Now, the units of moments are Newton meters because the units of force are newtons, and the units of perpendicular distance are meters. So the unit of moment are a combination of the units of force and distance, since the two values are multiplied. Now, moments are vectors as they make objects rotate. So when calculating moments, you must state the direction they cause rotation in. So the effect of a force causing an object to rotate is called a moment. The point at which an object rotates is called the pivot or the fulcrum. And we can calculate a moment with the following equation. Moment is equal to force times by perpendicular distance from the pivot. Now, the force in this equation must be the vertical force acting on the object. If the force is acting at an angle, then the vertical component of the force must be found. The horizontal component of the force will not be acting in the direction of rotation, so will not contribute to anything towards the moment being produced. So we can calculate the moment of a force about any point, not just a pivot. However, in solving problems, it's often most convenient to take the moments about the pivot, as there's often an unknown force acting through the pivot, its contact force on the object. So we can use the idea of a moment to solve two sorts of problems. Firstly, we can check whether an object will remain balanced or start to rotate, or we can calculate an unknown force or distance if we know that an object is balanced. Now, to work out this information, it's important to clearly label free body diagrams of the situation. So as mentioned before, we can get objects which rotate about a pivot to balance. So consider the following object which is balanced on this pivot. Now, what happens is multiple forces and moments will act on the body. Now, the physics behind getting an object to balance is called the principle of moments. So we know that these forces on the object will produce moments on either side of the pivot in this diagram. That's because the object is fixed at the pivot, and the forces will cause a rotational motion. Now, when an object balances, the moments on either side of the pivot must equal each other, because it means the moments will cancel each other out. The rotation they produce are in opposite directions, so they will cancel through, which is why it's crucial to remember that moments are vectors. So mathematically, you would say one moment is a positive value and one moment is a negative value. This means overall there is no resultant moment. So when an object is balanced, we say it is in equilibrium. Now, for an object to be truly in equilibrium, there must be no resultant moment or no resultant force. So this means that the moments on either side of the pivot sum to zero. And it also means the forces up and down on the object will also sum to zero. So for an object to be balanced, the moments and forces on either side are equal. So we can say the left-hand rotational effect equals the right-hand rotational effect, or the anti-clockwise moment equals the clockwise moment. Now we know that the moment is force times by distance, so in this example we can say force 1 times by distance 1 is equal to force 2 times by distance 2. So, to clarify, for an object to be in equilibrium, there must be no resultant moment or force on the object. So the sum of the moments clockwise about a pivot will equal the sum of the moments anti-clockwise about a pivot. So the force clockwise times by the distance clockwise is equal to the force anti-clockwise times by the distance anti-clockwise. So here we can see the principle of moments, that in this case the anti-clockwise moment equals the clockwise moment, or force 1 times by distance 1 equals force 2 times by distance 2 plus force 3 times by distance 3. This indicates to us that if there is more than one force acting on one side of the pivot, you work out the moment individually and then add them together to get the total moment on that side of the pivot. So here is an example of a moment calculation. Find the force causing the anti-clockwise moment in this situation. So we can say force 1 times by distance 1 equals force 2 times by distance 2. So it's force 1 times by 6 equals 10 times by 4. So force 1 is equal to 40 over 6, which is 6.7 newtons. So you write out your equation, you place your values into the equation, you work through the values and rearrange where needed, and give your answer to the same significant figures as the question with the correct unit. Here's another example of a moment calculation. Find the distance between the pivot and the force causing the anti-clockwise moment. So in this situation, we can say force 1 times by distance 1 equals force 2 times by distance 2. And then at that point, we can then say that distance 1 times by 15 equals 10 times by 3. So distance 1 equals 30 over 15. So distance 1 equals 2 meters. So once again, we'll place the values into the equation, we've worked through the values and rearranged where needed, and we've given our answer to the same number of significant figures in the question with the correct units. So to summarise in today's lesson, we've looked at the moment of force and the principle of moments. So if we've been successful and we've learnt in today's lesson, we should be able to describe the conditions under which a force produces a turning effect. We can describe the support force on a pivoted body, and we can understand the forces and moments on a body in equilibrium. So thank you for watching this video on moments, which is part of the Forces and Motion module for OCR A-Level Physics. Thank you so much and have a lovely day. Hello and welcome to this lesson on couples, which is part of the Forces and Motion module for OCR A-Level Physics. So in today's lesson we're going to be looking at couples and looking at how to calculate the properties based on laws of equilibrium. So if we've been successful and we've learned in today's lesson, we should be able to explain what is meant by a couple, calculate the forces on a body in equilibrium, and then calculate the moments on a body in equilibrium. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification: 3.2.3 equilibrium, in particular couples and the torque of a couple. Now, a couple are a pair of forces acting on a body that are of equal magnitude and opposite direction, acting parallel to one another but not along the same line. So forces acting in this way produce a turning force or moment, and the torque of a couple is the rotation force or the moment produced. Now it's important to note that the forces on this beam are a couple producing a moment or torque which will cause the beam to rotate. So examples of couples in the real world would include turning a steering wheel, twisting a bottle cap, or turning a spanner around a bolt. Now the factors that affect torque involve the magnitudes of the forces involved, the perpendicular distances between their lines of action, and the angles of the forces. So we can say that a couple is a pair of forces of equal size which act parallel to each other but in opposite directions, as you can see in the following diagram. As we mentioned before, a couple has no resultant linear force, as the two forces cancel each other out. So this means that due to Newton's second law of motion, F equals ma, this object would not actually accelerate. A couple, however, does produce a turning effect or moment as they are acting in the same direction, as you can see in the following diagram. Now, when the force is applied, the object will rotate with a constant angular speed, but it remains fixed in the same location. Now, the size of the moment, or torque, depends on the size of the forces and the distance between them. So what we can say is that the moment of a couple, or the torque, is equal to the force times by the perpendicular distance between the lines of action of the two forces, or m is equal to F times by d. So this occurs as the two forces produce a moment in the same rotational direction. So the moments produced needed to be added together to form the couple. So we can say that the torque of a couple is equal to double the magnitude of the moment of the individual forces. So a couple is a pair of forces of equal size which are parallel to each other but in opposite directions. The moment is determined by the perpendicular distances between the lines of action of the two forces. So this means that the horizontal component of the displacement needs to be calculated if the couple is at an angle. Now the forces given might not always be perpendicular to the distance between them, so as we said before, in this case remember to find the component of the force vector that is perpendicular by resolving that force vector. Now the forces that can make up a couple cannot share the same line of action, which is the line through which the point at which the force is applied. Now to answer questions on couples, use the following technique. The first step is to identify the forces on the object causing moments. If acting at an angle, ensure the force is resolved to the horizontal and vertical. Step 2. Always include the weight from the centre of mass if not explicitly stated. Then take the moments about one point. Ensure that this point is where a force is and ignore that force. Equate the clockwise and anti-clockwise moments and solve the equation based on this. Then the force, which was ignored previously, could then also be calculated using the equilibrium principle that force up equals force down. So consider the following object. The two forces in this example balance up and down, so it's 15 newtons up and 15 newtons down, so the wheel will not move up or down or sideways. But the wheel is not in equilibrium, because whilst there is no linear resultant force, the pair of forces will cause it to rotate. So what we can say is that the pair of forces act as a couple. A couple will have a turning effect but does not cause our object to accelerate. So to form a couple, the two forces must be equal in magnitude, parallel but opposite in direction, and separated by a distance d. Now the turn effect or moment of a couple is known as its torque. So we can calculate the torque of the wheel by adding the moments of each force about the centre of the wheel. So in this case, the torque of a couple is 15 times by 0.2 plus 15 times by 0.2, which is 6.0 Newton meters. We could have also found this same result by multiplying one of the forces by the perpendicular distance between them. So 15 times by 0.4 is 6.0 Newton meters. So to summarise what we've looked at in today's lesson, we've looked at the idea of a couple, the torque of a couple, and the equilibrium of an object under the action of forces and torques. So if we've been successful and we've learnt in today's lesson, we should be able to explain what is meant by a couple, calculate the forces on a body in equilibrium, and then finally calculate the moments on a body in equilibrium. So thank you for watching this lesson on couples, which is part of the Forces and Motion module for OCR A-Level Physics. Thank you so much and have a lovely day. Hello and welcome to this video on the centre of mass, which is part of the Forces and Motion module for OCR A-Level Physics. So in today's lesson we're going to be looking at centre of mass, and we're going to try to understand what is meant by the term centre of mass. So if we've been successful and we've learnt in this lesson, we should be able to understand what is meant by the centre of mass and the centre of gravity of an object. Understand that the centre of mass and centre of gravity of a uniform regular solid is at its centre, and then finally explain the link between the centre of mass and the centre of gravity and stability. So in today's lesson we're going to be looking at the following part of the OCR A-Level Physics specification: 3.2.3 equilibrium, in particular centre of mass, centre of gravity and experimental determination of the centre of gravity. So the centre of mass is where we assume all the mass and the weight of an object to be concentrated, as shown in the following diagram. Here, if the object has uniform density, we assume the centre of mass to be in the centre of the object. Now the resultant gravitational force on the object, its total weight, will act through a point called the centre of gravity. Now it's much easier to analyse and solve physics problems if we think about the weight of an object acting through its centre of gravity and not a collection of many tiny forces acting throughout the object. So at the centre of mass we draw a vector representing the weight, and this always acts towards the earth, so this is called the line of action. Now on a force or free body diagram, the weight of an object must be drawn at the centre of mass regardless of the object, so as you can see in the following diagram. Now this assumes that all of the mass is at this point, so it means that therefore all the weight is found at this point. So in this particular example, this would be an incorrect force diagram because we are not drawing the weight acting from the centre of mass. This would also be an incorrect diagram, and this would also be an incorrect diagram, but this would be a correct force or free body diagram illustrating the line of action of weight of an object. Now if the centre of mass is at the centre of the object, the forces on either side of it are the same, so the forces are therefore balanced. Now as we assume all of the weight acts through the centre of mass, this means our body is in equilibrium. Therefore at the centre of mass the forces on an object either side of it are balanced. So therefore at the centre of mass the turning forces or moments on the object either side of it are balanced. So this means that at the centre of mass the body will always be balanced. So if your centre of mass and therefore your line of action are inside the object's base, it is balanced. Now if the line of action is inside the base of an object, we can say our object is stable and will not fall over. So in this particular scenario our object is stable, or we could also say the object is in a stable equilibrium. Now this is because the forces and moments act on the object are balanced. Now if the line of action is outside the base of the object is unstable and will fall over. Now this will happen when the object is tilted, so this object is unstable, or we say the object is in an unstable equilibrium. So this happens because the moments are not balanced and there is a resultant moment acting on the object. So the stability of an object links to the position of the centre of mass and the base of the object. The lower the centre of mass or the centre of gravity, the more stable an object will be. And the wider the base of an object, the more stable the object will be. In both cases, this is because it is less likely that the line of action falls outside of the base and produces a resultant moment. So an object will be very stable if it has a low centre of mass or gravity and a wide base, and this is used in many designs such as racing cars. Now if we consider an object in stable equilibrium on a sloped surface, we can consider the following forces acting on the object. We have our normal contact forces for X and Y, the two wheels. We have our weight acting from our centre of mass, and we also have our frictional force acting against the motion. Now we know that in a stable equilibrium, the upward forces must equal the downward forces. So in this case, it will be the two contact forces, Msx and Sy, added together, and that will equal the W cos theta, which is going to be the vertical component of the weight in this particular situation. Now it's also important to note that Sx will be greater than Sy because x is lower than y, so there won't be an equal sized force. But also we know that in the stable equilibrium that the slope up forces will equal the slope down forces. So in this case it will be equal, the friction will be equal to W sine theta, so it will be equal to the horizontal component of the weight in this situation. Now the centre of mass of an object is the point located at the object's average position of all the particles of mass that make up the object. Now the average position of all the particles of mass of an object will be the geometric centre only if the object is symmetrical in 3 dimensions and homogeneous, so it has the same density at all points inside the object. Now for other objects, the centre of mass will not be the geometric centre, and in some cases could even be outside the object itself. Now we must be aware of how to find the centre of mass of different objects. Now there are different ways to find the centre of mass of an object. Now for all objects, the centre of mass is directly below a point where the object can be freely balanced. So an object can be balanced if the pivot is placed at the centre of mass. This happens as the forces and moments are balanced on either side of the centre of mass. It's in equilibrium. So in this situation, a pencil is balanced on a finger. Now we can see straight away our line of action from our centre of gravity, and we can note that the forces and moments on either side of this pivot are equal to the other side. Now, as we know that the centre of mass must lie in the same plane as where the object freely balances, the line of action of the weight, or the centre of gravity, is always drawn down from the pivot. Now you can find the centre of mass of a symmetrical object by looking at its symmetry. For a symmetrical object, the centre of mass lies at the point of intersection of the lines of symmetry. Now if we look at this following shape here, we can see our different lines of symmetry in the following diagram, and our centre of mass is at the intersection of these lines. So what you would do is draw in several lines of symmetry in an object, at least 3 or 4, and where they intersect or cross is where the centre of mass is found. Now another way to find the centre of mass of an object is that when an object is suspended and hanging freely in equilibrium, the centre of mass is directly beneath the point of suspension. So in this diagram here, the object is freely hung, and the hanger basket will show this because it is just hanging there in equilibrium. Now the centre of mass must lie somewhere in the plane of the point of suspension, which is shown with our line of action, and it's always drawn where the object is freely hung. So we know our centre of mass must be directly below where an object can hang freely, when an object just hangs with nothing else providing force. Now to find exactly where the centre of mass of the object is, you must freely hang it from several places and draw a line of action for each and see where they intersect or cross. Now, so to find the centre of mass for an object, you could, for all objects, the centre of mass is directly below a point where an object can be freely balanced. For symmetrical objects, the centre of mass lies at the point of intersection of the lines of symmetry. And finally, when an object is suspended and hanging freely in equilibrium, the centre of mass is directly beneath the point of suspension. So we can use this principle to determine the centre of mass of an irregular shaped object. Now this is useful in the real world as it allows you to understand how objects can be balanced. But this can be difficult in practice with complex 3-dimensional objects, but is easy to do with objects made from card. So the centre of gravity of a thin sheet or lamina of cardboard or metal can be found by suspending it freely from 2 or 3 points, as shown in the following diagram. Small holes are made around the edge of irregularly shaped objects, and a pin is put through one of the holes and held firmly in the clamp and stand so the object can swing freely. A length of string is attached to this pin, and the other end of the string has a heavy mass attached to it. This arrangement is called a plumb line. Now the object will stop swinging when its centre of gravity is vertically below the point of suspension. A line is drawn on the object along the vertical string of the plumb line, and the centre of gravity must lie on this line. Now to find the position of the centre of gravity, the process is repeated with the object suspended from different holes. The centre of gravity will be the point of intersection of the lines drawn on the object. Now you can check that the position of the centre of gravity is correct by removing the card and seeing whether it will balance on a pin or your finger at this point. Now we have a weight because of the force of gravity on the earth on us. So each part of our body, our arms, our legs, our heads, will all experience a force caused by the force of gravity. However, it's much simpler to picture the overall effect of gravity acting at a single point, which is our centre of gravity. So the centre of gravity of an object is defined to be the point where all of the weight of the object may be considered to act. Now, for a person standing upright, the centre of gravity is roughly in the middle of the body behind the navel. Now, for a sphere, it's at its centre. Now, as mentioned before, it's much easier to solve problems if we simply indicate an object's weight by a single force acting at the centre of gravity, rather than many forces act on each part of the object. Now, for a symmetrical object with a uniform density and a uniform gravitational field, the centre of mass and the centre of weight are in the same position. Now, as an object is made up of identical atoms, each with its own weight, the resultant gravitational force on the object will act through the centre of gravity, which coincides with the centre of mass. So the centre of mass is a point through which any externally applied force will produce linear motion, but not rotational motion. Now, on the Earth, the centre of mass and the centre of gravity for an object should be at the same point. Now, if an object's centre of gravity falls outside the base of the object, as mentioned before, it will topple as a moment is being introduced to the object. So to summarise what we've looked at in today's lesson, we've looked at the centre of mass, the centre of gravity, and the experimental determination of the centre of gravity. So if we've been successful and we've learnt in today's lesson, we should understand what is meant by the centre of mass and centre of gravity of an object. Understand that the centre of mass and centre of gravity of a uniform regular solid is at its centre, and explain the link between the centre of mass and the centre of gravity and stability. So thank you so much for watching this lesson on the centre of mass, which is part of the Forces in Motion module for OCR A-Level Physics. Thank you so much and have a lovely day.